Hello and welcome to Textbook Engineering Problem. Today we're going to be working out of Elementary Principles of Chemical Processes 3rd edition. We're doing problem number 2.24. I'll go ahead and read the problem statement. The following empirical equation correlates the values of the variables in a system in which solid particles are suspended in a flowing gas. Then they give the equation. I'll go ahead and write that down. Okay, so that's the relationship that they give to us. Both viscosity divided by density, diameter, and particle diameter, velocity, density divided by viscosity, are dimensionless groups. Kg is a coefficient that expresses the rate at which a particular species transfers from the gas to the solid particles, and the coefficients 2.00 and 0.600 are dimensionless constants obtained by fitting experimental data covering a wide range of values of the equation variables. The value of Kg is needed to design a catalytic reactor. Since the coefficient is difficult to determine directly, values of the other variables are measured or estimated, and Kg is calculated from the given correlation. The variable values are as follows. Okay, I'll go ahead and write these down. And then I assume that we want to use these values that they're giving to us in the equation that they gave to us. And in that case, we're going to need to put them all into standard units so that all of these relationships will work out units-wise. So I'll also go ahead and start working on that as well. So this is dp, that's the particle size diameter. They gave us 5 millimeters, and this equals 5 times 10 to the minus 3 meters. Y is a dimensionless number. D is another diameter. No, it's a diffusion coefficient. Excuse me. Centimeters squared per second. We're converting that into meters. That equals meters squared. Sorry, that's a little cramped. I can write that again underneath. It is 1.0 times 10 to the minus 5 meters squared. Okay, per second. Mu is the viscosity. That is already in the correct units. The density, rho, and the velocity is in good units as well. All right, so I now had to do a couple of conversions. Okay, so let's read the problem statement, part A. What is the estimated value of Kg? Give its value and units. Okay. Well, let's calculate what the right side of this equation looks like, given all the parameters that we were given. and then we'll be able to calculate what kg is. So we know that 2.00 plus 0.600 times, okay, let's figure out what these dimensionless numbers equal. Rho d, that equals 1.00 times 10 to the minus 5 Newton seconds per meter squared divided by, oh, I didn't convert this density. The density needs to be converted into units. Here we go. 1 gram cm3 into kilograms. And then centimeters. That equals 1.00 kilogram per meters cubed. Okay, back down here. Okay, Newton is a combination of a bunch of units. But since we've put everything into SI, we can kind of take a shortcut, and we know that this is a dimensionless unit and everything is in SI units. So Newton's actually equals force, which is mass times acceleration, which is meters per second squared. So that's what Newton's equals. Kilograms, meters, kilograms, meters, per second squared. Okay, so kilograms cancels kilograms. We got 1 meter here and 1 there, so now we're left with 2, and that cancels with those. And then we got 1 of our seconds canceling with 1 of those, and the newtons is canceled out. So then we're just left with meters squared per second, and that is what D is in. So let's write D is in 1.0 times 10 to the minus 5 meters squared per second. So all the units cancels out, like we said. They should. And our unitless combination is equal to 1. Because we have this cancels with this, and we're just left with divided by 1, so that's 1. Then we need to raise this quantity to the third power, which also equals 1. Okay, so we figured out what that term is. Now we need to figure out what our next term is. dp up rho u. This equals times 10 to the minus 3 meters u 10 meters per second. Rho is 1 kilogram per meter 3. And viscosity is 1 times 10 to the minus 5 Newton seconds per meter squared. Okay, I'm not going to go through all the units on this one. Just they're all in SI units. I could convert the newtons like I did last time, but I'm not going to go through that. They'll all cancel out to be no units, unitless. Okay, but the number does matter, so let's get our calculators out. And this number changes to 5 times 10 to the third power, and it's unitless. Now we look at what dpu rho over mu to the 1/2 equals 70.7 1. Okay. So now we know that kg dp y over d equals 2 plus 0.6 times 1 times 70.71. And get out our calculators again, and this equals 44.4 is 44.4 for what this equals, but we still need to calculate what kg equals. That's the purpose of the question. And it wants us to know what the units are as well. Well, if you look at the starting equation here, and back to the problem statement, it tells us that this group is dimensionless, this group is dimensionless, and then it also tells us that 6 and 2 are also dimensionless. So all of these things are dimensionless. Then this group, each term in this sequence, so term, I'll number them off. This is term 1, term 2, and then all of this is term 3. Then each of those, if term 1 is dimensionless and term 3 is dimensionless, in order to add them together, each thing has to have the same dimensions. So if everything on the right-hand side of the equation is dimensionless, then this group right here is also dimensionless. Okay? We know that there are no units here. It's dimensionless. It's easier for us to calculate what kg's units are. So if we know that kg equals 40, this group equals 44.4, then we know that 44.4 dimensionless times d divided by dp divided by y. We know that if we plug in these units, we're going to get what the units of kg are. So let's go ahead and do that. 44.4. What are the units of d? D is 1 times 10 to the minus 5. So that means meters cancels with one of those meters. And we now know that the units are meters per second. And let's pull out our calculators and figure out what the value of the magnitude of kg is. 0.889 meters per second. That is the answer to part A. Okay, part B. Why might the true value of kg in the reactor be significantly different from the value estimated in part A? Give several possible reasons. Okay, I'll give a couple of reasons. Well, this is an empirical function that they gave to us, so the estimated values that they give for the parameters 2 and 0.6, those could be significantly off. So if those estimates are accurate for one part of the equation, or at least for one regime, they might not fit very well for other parts of the regime. So maybe they fit well for a certain, maybe your normal operating conditions, but once your operating conditions change slightly, well, then those parameter estimates are not as good of a fit. And so now your calculation of what kg is could be significantly off and thrown off your estimation. Another reason that it might be off is the estimated values for the fluid properties might not be accurate. So there's a bunch of estimated values that they give to us, like the particle diameter and the diffusion coefficient and viscosity and density. Those are all order of magnitude estimations, so they could be significantly different, which could lead to a pretty big difference in kg. So there's a couple of reasons. Okay, that one's more of like a qualitative, do you understand what's going on kind of question. So let's move on to part C. Now we're going to have to move over to the computer in order to do this problem. Okay, so we've moved over to our computer here, and we are now going to do part C, which involves using a spreadsheet. Okay, so it says the problem statement, create a spreadsheet in which up to 5 sets of values of the given variables dp through u are entered in columns and the corresponding values of kg are calculated. Test your program using the following variable sets. 1, the values given above. 2, as above, only double the particle diameter, making it 10 millimeters. 3, as above, only double the diffusivity. 4, as above, only double the viscosity. 5, as above, only double the velocity. Report all 5 calculated values of kg. Okay, so let's just go ahead and start entering all these values. So they told us to put it in columns. Create a spreadsheet in which up to 5 sets of values given. Enter in columns and the corresponding values of kg. Okay, so we got kg over here, and now we need dp and y, d mu rho and u. Okay, so dp is equal to 5e to the minus 3. Y is equal to 0.1. D is equal to 1 e to the minus 5. Mu is equal to 1 e to the minus 5. Rho is equal to 1, and viscosity is equal, or velocity is equal to 10. And this is all in SI units. Okay, so now we're going to calculate what kg equals. Well, we'll say, okay, so this is the right side of the equation, which equals 2 plus 0.6 times, go in here and say mu divided by rho divided by d, and that is raised to the 1/3 power. And then we're multiplying that by dp times u times rho divided by viscosity. And that is the square root. Okay, so that's the right side of the equation. Kg equals the right side of the equation times d divided by dp divided by y. Okay, so I forgot to put parenthesis marks on the right hand side of my equation right there. So this term wasn't being raised to the 3rd power, it was just being raised to the 1 divided by 3. So make sure you put parentheses around that. Okay, and now our kg value looks to be the same what we calculated before. Okay, So this is number 1, number 2, number 3, number 4, and number 5. Okay, so scenario 2 said everything's the same, only double the particle diameter. Okay, so now we say this is doubled, but everything else is the same. How much does it change? Okay. Now, scenario number 3, all of the above, only double the diffusivity. Okay, so this is doubled, and everything else is the same as before. And in number 4, everything's the same, only the viscosity is doubled. Okay, and in the last one, everything is the same, only the velocity is doubled. Okay, so this let's get it so they all have the same significant figures here. Okay, so these are all of the kg values for those different scenarios. Great, and that is the end of problem 2.24. If I made any errors or mistakes in the problem, let me know, and I will try and make a correction to this video. Also, if there are any problems in this book that you guys are struggling with that I haven't gotten to yet, just leave a comment and I will try and make a video on that and help clear things up. All right, thanks for watching.